thank you again for coming tonight. We are pleased to have with us Dr. Jim Brau, all the way from Eugene, Oregon. Lucky to get out yesterday because I guess for never happens up there. They got snow yesterday, but he did want me to let you know his football team is #1 in the country, and that's why everybody should study physics because he's totally responsible for it. So go Ducks. So I've got a lot to share with you tonight. If you would please join me in welcoming Jim Brau.
Thank you, Christine. Good evening, everyone. I have been teaching astronomy to the football players for many, many years, and it's finally starting to pay off. Okay, so tonight I'm going to share with you an adventure that many physicists from all over the world are engaged in, which is really in the tradition of centuries of exploration here on Earth that reveals everything we can contribute to the knowledge of the universe. And so what I want to do is kind of trace through some of that and show you what's currently afoot in the field of physics. And of course, this is a beautiful photograph that was taken near Devil's Tower, which shows the Milky Way galaxy in the night sky, and many of us have had the pleasure of seeing that. So here on Earth, we are doing experiments to explore the physics that is responsible for this beautiful universe we live in. And currently, the largest project in the world is the Large Hadron Collider in Geneva, Switzerland. This is a image that was created by the people at CERN to give you a perspective of that collider. We're going underground to one of the detectors. It's called the Atlas detector. You'll soon see a young physicist walk through a cutaway version of this detector to give you a perspective of what it is. It's a very complex device that has the capability to measure many, many details of the interactions of colliding particles that are occurring in this detector. And hopefully by the end of our lecture, we'll have a little more appreciation for what that's all about. So we have this Large Hadron Collider illustrated here. It basically, this is a tunnel underground. You see here is Lake Geneva, near the town of Geneva. Here's the Geneva airport. And we have this very large underground ring that's illustrated by this red line. And there are accelerator devices that put particles up to energies that allow them to go into this very large ring. That large ring has a 17-mile circumference, 300 feet underground. There are proton beams of particles circulating in both directions. There are superconducting magnets in that ring that are held at a temperature of 2 degrees above absolute zero. They're absolutely close to the limit of what you can cool them down to, so that you can get the very large magnetic field, something larger than 100,000 times the natural field of the Earth. There's 10,000 megajoules of stored energy in that device once it achieves its design goals, which it's still working towards. And when that happens, these beams of particles will be colliding particle on particle 600 million times per second at an energy that is 14 trillion electron volts of energy, quite a bit more than we normally have around the household. The proton beam itself stores 700 megajoules of energy, and that's that's in the beam that's circulating around the ring. You wouldn't want to be hit by that. That's essentially the equivalent of a 747 energy on takeoff, all stored within that beam. And it's enough energy to melt a half a ton of copper if you just took that beam energy and let it go into a ton of copper, half a ton of copper. So this is an amazing device that's been created, and it's to study the physics, fundamental physics, that relates directly to our understanding of the very nature of our universe. Exploring these deep mysteries of the fundamental substances of the universe and the history of the universe. And I'm going to tell you a little bit about that as we go forward. We're expecting revolutionary discoveries. We have hints of new things that are coming, and we're expecting it to have an impact on our knowledge that's somewhat akin to the quantum revolution of the early 20th century. And I want to talk a little bit about that today. Some of the ideas and targets of this exploration are things called dark matter, dark energy, the Higgs boson, extra dimensions. We always learn in school that there's 3 spatial dimensions, and Einstein told us there's 4 dimensions, but in fact now scientists and physicists are considering the possibility that there may be even more dimensions to space-time. and they may be revealed possibly by high-energy accelerators, and then other new particles and forces that may be unanticipated, and we'll look for those. So what I want to do is sort of trace the history of physics and how this all fits into that tradition, that history. And I want to start a little over 400 years ago, just over 400 years ago, with Galileo, who was the Italian physicist and astronomer who first took a telescope and looked into the sky and found all kinds of interesting things out there, such as the craters on the moon, the moons of Jupiter, the phases of Venus, and the sunspots on the sun. But at the same time he was doing these explorations of outer space, he was also doing his experiments on Earth. And the famous experiment in which he pondered whether the force or the acceleration of masses would be equivalent or different depending upon the mass. At that time, it was a prejudice that thought if something is heavy, it should fall faster. And he went up there, he dropped these two masses, and let's see what happened. He discovered from Pisa, the Leaning Tower of Pisa, that in fact they fell to the ground at the same time, establishing a very important principle of gravity. But we want to take that further. We want to apply this kind of discovery. And along came, beyond that, was the next great scientist in this story that I'm telling, was Sir Isaac Newton, the British physicist who is often characterized as being the greatest genius before Einstein in the tradition of physics. And Newton looked at this evidence that had been accumulated. He considered the moon and its trajectory around the Earth. And he considered apples in trees. It's a story that everyone learns. And he looked at those apples and he said, gee, they fall to the ground. And he had a notion that somehow maybe he could relate these apples falling out of trees to what's happening with the motion of the moon around the Earth. And he thought about the forces that were involved. He had an aha moment. Many of us have had aha moments. I hope everyone here that's working for extra credit either has had one or will eventually have one. And he wrote down an equation like this, which is the equation for the force of gravity between two masses. He basically created a unification of forces. And one of the themes that I'm going to be developing in this lecture is unification. Taking seemingly different phenomena and bringing them together into a single unified description. So what he saw at the time was these apples and these planets, or moons and other objects in space, as having some kind of interaction, and he was able to unify this into a single description. So now we have unified gravity, the law of universal gravitation, which basically brings the celestial and terrestrial forces together into a single description. So that's an example of how doing physics on Earth enlightens us about the nature of our universe. Here's another example. What is the sun's source of energy? Well, in the 19th century, scientists were trying to figure this out. We know the sun is a very powerful source of energy. How can this be? How can it have so much energy? And at that time, of course, chemical reactions were the only thing that was known. And so one could actually take and predict from chemical reactions how long it would take the sun to use up all the energy that you can anticipate it has based on the mass of the sun. And it turns out it only lives for 20,000 years if you want to use up all that energy, if it's just chemical energy. Well, there was evidence on Earth for a much longer duration of the sun. Basically, the sun, it was known that the sun had been around for billions of years. So chemical reactions on the sun were not sufficient to explain what was going on. In the 20th century, we had Einstein's great discovery, theoretical discovery, that energy and mass are related to one another. You can basically transform mass into energy or transform energy into mass. And also at the same time, the discovery of the atomic nucleus and nuclear reactions. And out of that came, we won't go into the details of this, but a series of nuclear reactions that allows us to explain how we can get much more energy out of a reaction than we get from chemical reactions. And in fact, based on this, we have enough energy for the sun to shine for tens of billions of years. So these experiments on Earth give us the knowledge that allows us to understand how the sun could do what it does. Now that was based on relativity, E equals mc squared and all that. If you were paying attention to the slideshow at the beginning of the program, you know what one of the ways Einstein expressed this. He has a way of making things simple, easy to understand. What he said was, when a man sits with a pretty girl for an hour, it seems like a minute, but let him sit on a hot stove for a minute, and it's longer than an hour. That's relativity, according to Einstein. Anyway, that principle of relativity actually you can lead to equals mc squared. So, those are some examples of the distant past where we did experiments on Earth and we gained great knowledge that allows us to understand our universe. So here's the Large Hadron Collider. You see that collision. What we're doing at the Large Hadron Collider is colliding, let's do it again, protons, two protons come together. So we have these beams of protons circulating in the ring, and the beams means a whole bunch of protons. And every once in a while, actually a whole bunch of them once in a while, one of the protons from one direction will strike a proton from the other direction, annihilate, and release the energy. In fact, the E equals mc squared formula applies here. It basically releases the energy that's been stored up in those particles and can create new things. And we can look for new things. We can look for new types of objects, or we can look for new interactions. Now, to make this story complete, I have to go back to Hubble's discovery that the universe is expanding. This is an important part of this story. And you remember Hubble. He was actually trained as a lawyer, but then he got really fascinated with astronomy and became one of the greatest astronomers. And what he did was he looked out into space at galaxies. So this is a bunch of galaxies. So each one of those galaxies is billions and billions of stars. And as he looked out, farther and farther out, this is the distance to the galaxies. He made a plot. And this is how fast the galaxy is moving away from us. And he made a plot, and this is kind of the way science works. These don't fall on a straight line. They fall in a distribution, but you can see there's a trend. The farther out you go, the faster the galaxies are moving away from us in every direction. This is a very old plot. This is from back in those days. Today we go way, way beyond, and this trend just continues on. He had to base his conclusions about what was going on based on a little bit of data, and he saw this. And as a result of that, he had the first evidence that the universe began with a Big Bang. Realizing that today everything's expanding, if you turn the clock backwards, everything in the universe will come back to a very high density. And so this is kind of a cartoon that shows the history of the universe over almost 14 billion years, where you have an expansion taking place. And as the universe expands, everything in the universe is moving away. And so he found that evidence, and it made a prediction. If you go back in time, early on in the universe, all of this matter that we currently see distributed and moving away from us would have been condensed into a very, very hot, dense region. A fireball, if you like. Everything very, very hot and very dense. And only over billions of years did that material expand, condense into stars and galaxies and so forth, and life and everything else. And so what he predicted was, or what was predicted from the result of this, it wasn't really his prediction, it was others thinking about this, so when we look at the Milky Way galaxy in visible light, if we could actually look at it in microwaves instead of visible light, we should be able to see that fireball, because the fireball is moving away from it at very close to the speed of light. And if you understand the Doppler effect, you'll realize that that light then gets shifted in color from visible to microwaves. In fact, in 1975, these microwaves were discovered. They were discovered and confirmed the Big Bang theory of the universe. They were predicted by Hubble's discovery, and they basically were the confirmation that now, for the last 45 years, has been the paradigm in physics and astronomy of the nature of the universe. And many, many experiments have been done to measure the properties. It's a very, very uniform fireball, it turns out. If every direction you look, you see the same microwaves coming at you. And that's another mystery, another interesting thing that people try to understand. But there is that, if you could look up at the sky with very sensitive microwave eyes, you would see this radiation. It's quite a phenomenal thing. So we have this history of the universe, and this is a little cartoon that shows you, in function of time, coming out to today, which is almost, we're getting close to 15 billion years. I don't think any of us in this room, no, the youngest people probably won't make it. But we're up to about 13.7 now, and we've got a few more years to go before we get to this point. But as we go back to 300,000 years and so forth, we have this history. And notice here, we have lots of particles illustrated here. That's because in that early time, what was really going on was just particle physics. Particles were floating around, and that was really what was going on. We didn't have stars and galaxies and so forth. Right about here, let's see, right there, that's where we look when we see that microwave fireball. We're basically looking at a fireball that exists 300,000 years after the Big Bang. And of course, when we look out into space, we're looking back in time because it takes light time to travel over that distance. So in fact, we see that fireball, but it's been traveling for nearly 15 billion years when we see it. What the particle physicists are doing now are really studying the properties of these particles. And the universe is made out of particles. Our studies are revealing the nature of that early universe. And what we know is the atom has a nucleus. This was discovered a long time ago by Rutherford and his friends. And that nucleus is made out of nucleons, protons and neutrons, call those particles. And those protons and neutrons are made out of quarks. And of course, here at Jefferson Lab, studying the details of this is one of the main themes of the lab here. In the atom, we also have an electron in orbit around the electron. And that electron and the number of electrons and all the structure there is basically what determines the chemistry of these atoms. So that carbon and iron and gold, they all have different properties. Now, the electron was it's really attributed to a discovery by J.J. Thomson over 100 years ago. And some of us remember these cathode ray tubes because we had television sets which were based on cathode ray tubes. You basically make, it's called a cathode ray, which is basically a beam of electrons. And what he was able to do is to control this, use fields to move it around, and in so many ways developing the early principles of the television, but he really was motivated just to understand what is this electron, to discover the electron, to learn as much as he could about it. Well, many years later, after he won the Nobel Prize, became famous for doing this fundamental science, and electrons were everywhere in common use, he was quite proud of this and quite amazed with what an enormous impact that it had on the world. And so I'd like to play for you a statement that he made in 1934. Here's a statement that J.J. Thomson made about his discovery.
Could anything at first sight seem more impractical than a body which is so small that its mass is an insignificant fraction of the mass of an atom of hydrogen, which itself is so small that the crowd of these atoms, equal in number to the population of the whole world, would be too small to have been detected by any means then known to science.
So I think one of the messages I want to deliver is it's more impractical. When he was working on this to discover the electron and to begin playing with the electron, it was basically pure science, just out of curiosity to understand what this thing was. And today we've gone many, many generations in developments of new applications of this, which were unimaginable, and already by 1934 he was himself quite amazed by it. Okay, so let me now turn to the 20th century. And in the United States, the two major laboratories in the 20th century for doing particle physics were the Electron Linear Accelerator at Stanford, called SLAC, and the Proton Synchrotron and Fermi Lab near Chicago. I want to just illustrate how these two contributed to our understanding of the structure of matter, which also bears on our understanding of the structure of the universe. At the linear accelerator at SLAC, and I've just lost my sound, but I hope you can hear me in the back. Did I do something? No. Can you hear me? This is a high energy accelerator that is sort of a cousin to the JLab accelerator, which is also an electron accelerator. And at that accelerator, what was done seminally was to take, around 1969, or that's when the results were announced, take that electron beam, pass it through the proton, and to look and see what happens. And what was found was, you put it through there and it doesn't do much, but occasionally you get a deflection at the large angle of that electron beam as it passes through the proton. What does that mean? Well, that means there's point-like objects inside the proton. And those point-like objects we call quarks. And these were incredibly important development to understand that they actually exist, because there was speculation at the time that they might exist, but to actually see them in reality was a major discovery, and it led to Nobel Prize awards. Today at JLab, there's continued exploration of this and refining and in great detail understanding the nature of this, and much in the tradition of what was done at SLAC in those early discoveries. In 1995, another quark was discovered at Fermilab. This is the heaviest quark that's ever been discovered, and we believe it's likely to be the heaviest quark that exists in nature, but we haven't ruled out the possibility there's heavier ones yet. And what was done there was to collide head-on beams of protons and antiprotons, and there you see them passing by one another, and they don't always collide, they sometimes miss. But then every once in a while, bam, they collide, and what was discovered was that occasionally they would create these very heavy quarks called top quarks. This is a top quark. When you see a bar over it, that's an anti-top quark. Every particle we found so far in nature has an antiparticle associated with it. What was done here basically, again, is apply Einstein's equation of E equals mc squared, because the energy of these beams is being converted into this very, very heavy top quark. Okay, so coming back to our model of the universe, we have the Big Bang, we have all these particles early on, and we have a picture of the particles that exist. We have these quarks. The quarks that were discovered in that SLAC experiment are the light quarks up and down, which are actually the quarks that make up the proton and the neutron of the nucleus, or dominantly do. There's other small amounts of these other things, but mostly it's up and down quarks. And we have the top quark, and then we have a total of 6 quarks in nature that have been found. We also have, this doesn't show too well, but here's the electron, and we have the neutrino, which is related to the electron, and then we have also 6 particles that are electron-like, heavier particles that we've discovered. And we think that this is basically all there is in nature, but we're yet to see. And then we have force carriers, particles that carry force. So here's the photon, and many of you have learned about the photon. It's basically the carrier of the electromagnetic force. We have the gluon, which is the carrier of the strong force that binds the nucleus together, and we have particles that are responsible for radioactive decay, which is very common. So I want to talk a little bit about the interactions that these particles undergo, because this is an important part of the development of our science. First of all, gravity, which doesn't actually show up on this table, is by far the weakest of all forces. We saw that Galileo and Newton were playing with gravity and understanding it. It's very, very weak and doesn't really have an influence on the way our fundamental particles behave in the regime which we're usually studying in the energy physics laboratory. Then we have electromagnetism, which is, this is the force carrier here. We have the weak nuclear force. That's the force that I said was responsible for radioactive decay. And the Z particle and W particle are responsible for that. And then we have the strong nuclear force. I've listed these forces in more or less an order that represents, to some extent, their strength. The strong nuclear force is called strong because it's strongest. gravity is the weakest. Now, if we go back and trace the development or understanding of these things, say let's start with 1850. Well, in 1850, we had gravity, we had electricity, we had magnetism. By 1864, Maxwell had unified electricity and magnetism into a single understanding of something called electromagnetism. That was a tremendous unification, and it's much in the tradition of what Newton had done with gravity when he unified celestial and terrestrial magnetism. So by 1950, we had just gravity and electromagnetism, but now two new forces had been discovered in the first part of the 20th century, which are the nuclear forces. And so we had an increase in the number of forces that we have to understand. By 2000, we had actually unified the weak force with electromagnetism. So electromagnetism turns out to be a cousin of the force that's responsible for radioactive decay. And in fact, we can write down well-established and accepted theory that includes all of these things together. Another case of unification, and our next discovery we expect is to discover Higgs bosons at accelerators. The Tevatron at Fermilab is looking for this. The LHC will look for it as well. And we really expect to find something like a Higgs boson. We don't know exactly what its character is going to be, but we expect to find something. And when you get these unifications in this scale, we expect them particles. Our ultimate goal is to unify all these forces into a single force. We have a sort of a prejudice that says it's too complex to think you have all of these different distinct forces. And our history tells us that as we work hard enough, we can find ways to relate them together. And our current theories tell us that if we can find that magic formula to combine these, all these forces are going to be related. There'll be new particles coming out if this happens. And in fact, at Jefferson Lab, there are actually searches being done for some of the light new particles and some variations on this unification. And there's people working on searching for various kinds of new particles that might exist. So stay tuned on that. Hopefully one day that'll happen. Now, what is matter? What is matter? Well, we've been talking about the atoms and how it combines. Here's a whole bunch of things that are seen in nature. We have the sun, and we have planets, and we have buffalo. And we have the Willamette meteorite, which was stolen from Oregon and now sits in New York. And we have cosmic rays from outer space that are penetrating us all up the Earth all the time. All of this matter is what I would call atomic matter. It's made out of those quarks and electrons. You can explain all of this matter based on those quarks and electrons. However, it turns out that the atomic matter is really a fraction, a small fraction of the matter in the universe. What do I mean by that? Well, it turns out there's a halo of dark matter surrounding the galaxies in the universe. It's sort of illustrated by this little cartoon. There's a galaxy with all of its globular clusters, and there's kind of a dark matter halo surrounding it. The reason we know that's true is when we look at how stars in a galaxy rotate around a galaxy. So this is supposed to be a galaxy with all the stars, and we're looking at those stars, and we're watching how they move. We can predict what the orbit should be if we knew how much mass was attracting those stars to the center of the galaxy. We can predict how they should move, and we can see how much mass there should be there. So we can do a calculation as to how fast they should move, and that's what we'd expect to see. But in fact, what we end up seeing, if you look carefully here, you'll see these stars are actually moving faster than what we expect. And what that means, if you think about it, is something is pulling them in and keeping them there, because if they're moving faster, they would tend to want to escape. You get faster and faster in an orbit, you're going to go to a larger orbit, and eventually that orbit is going to become so large that you're just going to escape away. So what is concluded from this, and this is work that was done in the 50s, is there's an invisible material, and this is one of the evidences that tells us that there's some invisible dark matter out there that's pulling things together. There's lots of other evidence for this as well, such as, even before that, this is a cluster of galaxies. So it turns out that stars group into galaxies, and galaxies group into clusters of galaxies, and clusters of galaxies group into superclusters, and gravity kind of pulls things into some order. Well, this guy here, Fritz Zwicky, was looking at the motion of these galaxies in this cluster, and he found that they were moving too fast to be explained by the pull of gravity between the visible amount of mass in those galaxies. There had to be more mass that was pulling them at a higher speed. So he concluded at that time that this was a mystery and maybe there is something. And the evidence just keeps building up. In the 50s, we got these rotation data and so forth. So we know there's this dark matter. And we know that the dark matter actually dominates atomic matter. So in fact, if you do the measurement, what you find is that the dark matter of the universe outweighs the atomic matter by about a factor of 5 to 1. So that tells you we don't really know very much about what the universe is made out of. Because the atomic matter is the stuff we really know, we really understand, we know how to make all kinds of calculations, we know how to make eggs and whatnot. And yet it's only 1/5 compared to the dark matter in the universe, which is everywhere, including here in this room, by the way. There's dark matter in this room, but we don't see it, we don't feel it. At least this is what we currently think. We haven't found it yet, so we may be wrong, but that's what we think. So the real question is, what is it? We want to find it. We have good ideas, but only direct evidence of this will be definitive, and our accelerator experiments are aiming to find out what that is. Now there's one, just as an illustration, I want to give you an example of one way that this dark matter might be explained. This is an example that a number of theorists believe, and they call this a candidate theory, that could explain dark matter. It may be wrong, but it's worth thinking about, and I don't have time to go through a lot of other theories. But this theory called superstring theory, and basically unifies all the particles and all the forces. It unifies gravity with quantum mechanics. And we've been talking about unification. Physicists really have some kind of deep-seated belief that we should be looking for ways to take disparate, unequal things and making them into one. And the basic idea of this is that all particles are actually vibrating strings. So they're not actually point-like objects that we normally think of and that we actually see when we look at them. They're, in fact, vibrating strings. The only thing is, they're tiny. They're little tiny strings. So when we look at the particle with our microscopes that we can actually use, which are actually particle accelerators, we don't see this part of the string structure. We only see that it's a little tiny object. It sort of looks like a particle. But deep down, if you can get to a very, very small scale, the trouble is the dimension of that scale is 10 to the minus 25th times the atomic dimension. So it's so small that we have no practical means to get to it currently. But it has this idea, this theory has a lot of nice properties, and it also creates a whole new set of particles called superpartners of ordinary particles. Now you may know that back in the early part of the 20th century, when Dirac was trying to figure out the properties of the electron, he hypothesized that there should be antiparticles, that every particle should have an antiparticle. And in fact, that turned out to be the case. And we now know that every single particle has an antiparticle. And he theorized that basically just on trying to figure out what made sense in terms of explaining the experiments that were going on. So if this turns out to be true, and I'm not here to try to persuade you it is, I think it's a candidate to be considered, we may have a repeat of history where we have another set of new particles. Every particle gets matched by an ordinary particle. And our little cartoon of the atom then would tell us that, in fact, this quark is actually a vibrating string, this electron is a vibrating string, and the reason quarks and electrons are different is because they vibrate a little differently. And the properties then are explained by that. So maybe history will repeat itself just as the antimatter. And the thing is, one of the supersymmetric particles, those so-called particles that have just been predicted, actually has the properties that you'd expect of dark matter. So if this theory turned out to be correct, then dark matter would have been produced in the early universe, and it could explain why we don't see it. It actually explains all these properties. So just to drive this home, this pie represents all the stuff in the universe. Here's the atoms in the universe. here's the dark matter in the universe. You see it's about a ratio of 5 to 1. Don't grade me on that. But now we have another mystery, and that doesn't fill the pie. So what the heck is the rest of this stuff? There's not enough matter, either atomic matter or dark matter, to make up the stuff of the universe. There has to be something else. And that something else has been discovered, at least good evidence of that, what that is, has been discovered by looking at distant supernovae. So here's some galaxies that you can barely see. These are galaxies, and if you watch them, what happens is they have a bright spot that shows up near the galaxy, and these bright spots are stars that have exploded into supernovae. Now the reason these are useful for what I've just been describing is they are what we call standard candles, namely they have a brightness that is well defined. It's like if you have a match that you know exactly how bright it's going to be and you take it farther and farther away, you'll see it fade away. And if you look at something and you know exactly how bright it should be, then you can basically tell how far away it is by how faint it looks. And so these objects were used to look out into space. Here's another model of the expanding universe from the Big Bang to today. And using these distant supernova, it was determined that not only is the universe expanding, but its expansion is actually accelerating. In other words, it's expanding at a higher and higher rate all the time. Accelerating universe. It turns out that we think something called dark energy, and it's great to have a name for something you don't understand, because that's basically what we're dealing with here. We don't understand what this dark energy is, but we can measure what it is. We can measure it, and it turns out to be just enough to fill out this circle. What the heck it is, we don't know, but it makes a nice picture filling the universe with the dark energy and the dark matter. So if anybody tells you they understand what dark energy is, I don't think you should trust them. Anyway, the moral of the story is that the dark side controls the universe. If you looked at that little pie slot, you'd see the ordinary atomic matter doesn't have much of a role in this. The dark matter actually holds the universe together because it's pulling. It's basically acting just like all the ordinary matter. Gravity of all that dark matter is holding things just like the atomic matter is, and the dark energy is pushing it apart. So the dark energy basically controls the destiny of the universe. Now, dark matter is strange, and as I just said, dark energy is strange. But these are two of the mysteries that we are currently confronting, and we're hoping that our accelerator experiments will help us to learn some of the details of these things. So here's our Large Hadron Collider. This is here's Lake Geneva. Here's the Geneva Airport. This is a drawing of the surface above the Large Hadron Collider. You basically have a ring here that's about 5 miles, or a little more than 5 miles in diameter. And that facility is now operating, circulating beams, and there's several detectors that are sitting at points at which the beams can be colliding. And this is an example of one of those types of things that can happen, the way the Atlas detector would measure and see events. And we get lots of very smart graduate students to try to figure out what this means. And hopefully we'll discover some of these new phenomena we're looking for, or something to replace them. This facility has been operating for physics since last year. There was a slow startup, as you probably know, and we'll continue to run at least through next year, and maybe at least through the current period through next year, and then we'll continue for many, many years with downtimes to improve its performance. So we're searching for dark matter, for the Higgs bosons, which are actually something I didn't have time to talk about today, but it's really the principal reason the LHC was built, to look for the particles that are responsible for either the unification of electroweak force, electromagnetism, and the weak force, or in some ways we think of it as a breaking of those forces apart, or other new particles and forces. We hope, in fact, that we will find other new things that we haven't anticipated, that are just kind of speculating on. In the future, there's a a plan worldwide to develop what's called a linear collider. This would be an electron collider, which would be very complementary to what the LHC does. And it's in a straight line because you have to, it turns out electrons, as people here at Jefferson Lab will know, radiate when you take them around the circle or any bends. So we have to use a straight thing, and this is an illustration of that. We have a very long linear collider colliding electrons and anti-electrons together, and hopefully following up with the discoveries of the LHC. So that kind of brings me to a few concluding slides. The scientific goals of the LHC and the ILC are these dark matter particles, the Higgs boson, which is responsible for the mass of fundamental particles, and the force differences between the weak nuclear and electromagnetic force. Again, I didn't have time to go into the hidden extra dimensions, but I should have mentioned when I talked about string theory that, in fact, string theory predicts that there are many more extra dimensions to the universe than what we actually sense. And the way we can explain that is that perhaps the universe only expanded into 3 spatial dimensions, and those other extra dimensions are still tiny. They haven't expanded the way everything else has, but they may still be around. And if we penetrate deeply enough, we may actually be able to be sensitive to very, very short distances in these extra dimensions. It would be, the whole universe could be expanded into a very small distance. New forces, which we speculate about, and new fundamental particles. So, in conclusion, the Big Bang occurred 13.7 billion years ago. The universe has expanded and cooled. The fundamental particles have condensed into structures. The accelerators are revealing the fundamental particles and interactions. The dark matter dominates the mass of the universe. It controlled the early evolution, and it continues to impact today, as we see from the rotation curves and everything. And the dark matter discovery could come from the next accelerator experiment, such as the LHC, and maybe beyond that, the ILC. Let me just close with some quotes to inspire people about all of this. I think these are quite nice quotes from Einstein. One thing I've learned in a long life, that all our science measured against reality is primitive and childlike, and yet is the most precious thing we have. I really believe this statement. And finally, the most beautiful experience we can have is the mysterious. It is the fundamental motion which stands at the cradle of true art and true science. And one last slide. I would be amiss if I didn't quote the person that this lab was named after, Thomas Jefferson. He said, "Nature intended me for the tranquil pursuits of science by rendering them my supreme delight." Thank you all very much.
And we have a few minutes for questions.
So how exactly do you measure the rotation of galaxies?
Well, so the question is, how do you measure the rotation of galaxies? Well, it turns out that you use the spectrum of atoms. So atoms have, quantum mechanics tells us that atoms have electrons in only specific energy levels, and when light is emitted by those atoms, it only comes off with certain frequencies. Okay? So if you have an atom in the laboratory at rest, there are transitions between the electron states of the atom, and those transitions represent specific energies of the light that comes off, and that's a specific frequency. So if you look, if you look at the spectrum of light, you'll see lines in a spectrograph. Now, if that atom is moving, there's a Doppler shift. If it's moving away from you, all of these lines get shifted to the red. They become more towards the red part of the spectrum, visible spectrum. And if it's moving towards you, they get shifted towards the blue part of the spectrum. Okay. So now, if you look at and of course, the material of these galaxies is just normal, ordinary atoms, which have to emit radiation as atoms emit radiation. So you can look at one part of the galaxy, and you can see that it's redshifted, and you can look at another part of the galaxy, and you can see that what lines are blue shifted, and from that you deduce there's a rotation of the galaxy. Is that clear?
Well, what sort of certainty do you get with that data?
Very, very good certainty. I mean, there are many, many galaxies have been measured, And there is a set of curves that have a very common tendency to stay to high velocities as you go out away from the center. And many, many galaxies have been studied, and they're all more or less consistent with this general pattern. So we believe, this is a general feature of these galaxies. There is a competing notion as to what might be responsible for this, which is that we don't understand the force of gravity, because our basis of expecting the curve to have a certain shape, falling off as you go away from the center of the galaxy, is based on what we believe the force of gravity should be over long distances. And so there are some people who contend that the force of gravity, they have a different character over very long distances. But I think that's a small subset of physicists, and there's, in terms of this dark matter hypothesis, there are many consistent other examples, such as the motion of the clusters of galaxies, and also the measurements of the cosmic microwave background. That fireball in the sky actually tells you something about the dark matter content. So I and most physicists would favor the explanation that this is caused by the presence of dark matter in these galaxies. Did you have a question? No, you just scratched me.
If CERN is unable to find any evidence of a Higgs boson, what does that do for unification theories?
Okay, so basically what we know is that our theories tell us that the interactions get stronger and stronger as you go to high energy, and our theories break down when you get to basically the limit of what the LHC can reach. Our theories will no longer be valid. Something has to happen. It may not be the Higgs boson, it may be something else. It would be completely unphysical for there not to be something occurring. Whether the LHC misses it is, it's possible that it could miss it. But there has to be some phenomenon that fixes our theories, because our theories become unphysical at the highest energies of the LHC. And the Higgs boson is kind of the simplest, natural, nice little picture of this. But there are other possibilities of strongly interacting particles and perhaps new particles that would be related to that.
And what's the time frame that's expected?
Well, so the LHC is not going to be really sensitive to the discovery of the Higgs for a few years, and it really depends very much on whether the Higgs is of more easy masses to find or more difficult masses. If the Higgs boson is very light, close to the current limits that we know, where we've searched up to a certain point, it has to be heavier than that. If it's close to that limit, then it could take several years to actually be sure that it's not there. If it's heavier than that, it would be a few years to make that discovery. And in fact, a more early physics that can be discovered with the LHC would be these dark matter particles. If they happen to be in the range that's currently being investigated by the LHC, then those could be among the first discoveries made on a shorter timescale. And there's optimism that maybe something could break in the next year or so, not break physically, but break in some symbolic sense. So who's got an extra credit question? You got an extra credit question?
No, but I just have a radio.
Huh?
I just have a radio question.
Okay, let's go for it.
Why does the collider have to be underground?
Why does the collider have to be underground? Well, we should ask someone who designs colliders, but basically you do have radiation in the collider, and you do want to be isolated from the radiation of the collider. So that's one reason for putting it underground. Okay? Yeah. Yeah.
You said that every particle has an antiparticle. What would be the antiparticle of the neutron?
So the question was, every particle has an antiparticle, and the question is, what would be the antiparticle of the neutron? And I have a very, very brilliant answer. It's the antineutron. The antiparticle of the up quark is the anti-up quark. The antiparticle of the down quark is the anti-down quark. And the antiparticle, so most particles don't have another name. It turns out the positron is special because it does have another name. It's both the anti-electron, you can call it the anti-electron, or you can call it the positron. But we don't go around making new names for all the antiparticles. We just call them, maybe we're too lazy, but we just call them, anti-whatever. Okay? So, yeah, they're red in the red shirt.
How does a person conclude that something comes from nothing when it originally had to begin to expand into something? Like, we're talking about the expansion. But
so, you're talking about the Big Bang?
Yes.
Well, I didn't say it came from nothing, did I? All I said was that if we go back 14 billion years, or actually we can measure what's one of the remarkable things that's happened in the last few years is we've actually measured the age of the universe to within a couple of percent. And we know it's 13.7 billion years, looking at that fireball. And all I'm saying is that 13.7 billion years ago, all the energy of the universe was compressed down to a very, very small region. I don't know where it came from. I'm not arguing where it came from. That is a really interesting mystery that I'd love to try to figure out how to explore. But we know it's expanding today, and we know we can see that fireball, which, see, one of the great principles of science is to have a prediction before you see something. And that prediction of the fireball was made before it was discovered. In fact, it was accidentally discovered by a couple of guys working for Bell Labs, trying to create the most sensitive radio instrument they could, back in the 60s. And they had this noise in their instrument that they could not get rid of, and they tried everything they could think of to get rid of this noise. You probably had this experience at home where you had a buzz that you couldn't get rid of, and it just dries you out. Well, these guys were expert engineers and physicists, and they couldn't get rid of this noise, and they discovered it by accident. And what they then discovered after they came around and told people about this was that it had been predicted already, and there were other people preparing experiments to look for it, and they just found it by accident. They got the Nobel Prize for that discovery of that fireball. So I'm not saying where it came from. I don't know where it came from. I'm just saying that it was there 13.7 million years ago. Okay, question?
Maybe elementary, excuse me for this. When you're, excuse me, when you're making pouring water into an ice cream tray, which freezes faster, hot water, room temperature, or cold water?
Oh, who put her up to this? Which freezes faster? Just if you start with the hot water and you start with cold water? Well, the cold water is going to freeze faster, I think. But, does anybody want to? Okay. I think if you put them in the same conditions, it's going to be the cold water. Because you have to basically come down to that point with the hot water before you can freeze. Okay, if you change some of the conditions, then it could be different. There's a question up here.
If the gravitational force is the weakest force in the universe, then why is that what brings the galaxies together, not the electromagnetic force with the strong?
Well, that's a great question. So why does gravity work so effectively on holding all these astrophysical bodies together? And the reason for that is because it's a long-range force. It basically reaches out over very, very large distances. And the other forces don't do that. They're very much shorter range. The nuclear force, the strong force, pulls things into the nucleus and gets sort of concentrated just in the nucleus. And the weak force is even a shorter distance, well within the nucleus and responsible for radioactive decay. And the electromagnetic force gets canceled out by equal charges. So if you had an electron all by itself, it also would be a very, very long-range force and could have influences over large distances. But we know we have basically equal amounts of positive and negative charge floating around, and they come together and cancel each other out. But we don't have that happening with gravity. At least this is our current understanding of, our long time, many centuries understanding of gravity. And it stretches out over long distances. There's no way to cancel it out. So it basically is the force that's responsible for very large distances.
Can we thank our speaker again one more time?